So let's go all the way to this paper right here. So the actor-critic model of basal ganglia, and kind of go into some of the key points of this paper, right? So essentially, this is the paper that builds the link between actor-critic, reinforcement learning, and neuroscience. So that essentially there's a certain region of the brain that acts in certain ways, that has certain operations, and that aligns very closely with a certain segment of foundational uh, reinforcement learning, right? Okay. So, large number of computational models of information processing in the basal ganglia have been developed in recent years. Prominent in these are the actor-critic models of basal ganglia functioning, which build on the strong resemblance between dopamine neuron activity and the temporal difference prediction error signal in the critic, and between dopamine-dependent long-term synaptic plasticity and the striatum, and learning guided by a prediction error signal in the actor. We selectively review several actor-critic models of the basal ganglia with an emphasis on two important aspects: the way in which models of the critic reproduce the temporal dynamics of dopamine firing, and the extent to which models of the actor take into account known basal ganglia anatomy and physiology, right? So why is that important, right? Why is it important that we know some of the basics as to how these systems operate? Because when you know things like this, when you know the building blocks of how the brain operates, you can now actually build and reliably test more intelligent systems that are much more efficient as well. So, for example, there is a certain neuromorphic platform which is pretty much separate from everything else on the market. So the way the market setup is right now is it's mainly GPU focused. Then you have TPUs and other systems that are more specialized and much more or much better for training these neural networks, which the majority of the neural networks on the market that are being used in corporate settings are large language models, right? And then you also have other markets that are much more theoretical. They're not really necessarily in the prime time right now. However, they have a lot of promise. So you have the photonics, you have the neuromorphic, and you have the quantum, right? So neuromorphic computing, when you drill into that, there's going to be multiple different ways that you can actually sort of implement the basics of neuromorphic computing. It's going to be brain inspired. You're going to have a much different training modality and much different way of running inference on models as opposed to the industry standard, which again is on GPUs. So, for example, we'll take like an energy-based model or a latent variable energy-based model. So these kinds of models, they're not really very compatible with traditional GPUs. It's just that the way that they're designed, like their inherent characteristics, they just don't mesh well with GPUs at all, and it takes a lot of time and energy to get them to basically work at like a fraction of the effectiveness as transformers. However, they do show promise in certain tasks. So, for example, you can actually take an energy-based model and use it to control a vehicle, right? Now, again, when this first came out, I believe it was like around 2016, like around 2012 to 2016, when it first came out on the market. Again, it kind of ran into the same issues. So even though it was shown that it was possible to have these energy-based models controlling these vehicles, at least at that time, it just wasn't really all that effective, and you would never use an energy-based model over a convolutional neural network. Like that's pretty much the industry standard for right now. Even though theoretically there are certain models that have the potential to be a much better fit than convolutional neural networks. Again, they've been used for decades and decades at this point, so there's a ton of literature and a ton of information that you can draw upon and really get something going, right? So that's just all that to say. Pretty much again, why is this important? Why is it important that we understand that there are certain connections, there's certain links between certain modalities, whether that's reinforcement learning, whether that's representation learning, whether that's causal inference, so on and so forth. Just because we want to build better systems. We want to build more intelligent systems, and we want to do this in a way, if we can, knock out two birds with one stone. Um, at the same time, we're building more intelligent systems. We're also learning how the human mind works as well. So I just went through all these paradigms, and I'm just going to go and give a brief overview of each one in order. And pretty much how far does this push us along in sort of the idea of like HLAI or like human level AI, right? So first one right here, we're gonna go all the way to 1995, right? So the core idea is to map the reinforcement learning critic onto midbrain dopamine neurons, so compute a prediction error, and the actor onto the striatum slash corticostriatal plasticity. Use that error to tweak action policy. It's the conceptual blueprint trying TD style, that's temporal difference style reinforcement learning to BG anatomy, right? So what's new versus earlier, explicit brain level assignment of actor-critic rules, or excuse me, roles. So what's the main limitation? It is largely a hypothesis framework, not task-rich, fitted model, and little behavioral breadth. So it's not able to sort of adapt to new stimuli very easily, right? All right, so second iteration will be around 1998 to 99, right? So temporal difference, dopamine in action. So the core idea, a neural network with a temporal difference like critic that reproduces hallmark dopamine dynamics. So that is a phasic burst shift from reward to predictor, and you can train an actor to master sequences and delayed response tasks. All right, so what's new? Concrete simulations where the DA-like TD error teaches actions over multi-step sequences and matches recorded DA response properties. Limits still simple task, model-free learning only, no explicit state inference or planning, right? So there have been a couple of different frameworks that have came out in recent years. About 10 years ago, I believe now, probably like 10, 15 years ago, I believe the first iteration of like active inference was released by Carl Friston. So he's been in sort of the space for basically building out ideas of intelligence or frameworks for intelligence since like the early 90s. He's been in space for a very, very long time. However, I believe it was about 15 years ago when he sort of formalized and put everything into a specific framework called active inference, right? And it's pretty controversial. A lot of people like it, a lot of people hate it, a lot of people find it a little too cultish. I haven't seen too much or too many interviews of him specifically. It's mostly just like other people talking about him. So I definitely need to like look into his own interviews and kind of get his sort of like from a first hand, the person who built and put everything together, how he sort of interacts and how he sort of takes in new information. But I do like, some of the ideas in the active inference framework. One of them being basically the idea that you can mathematically model the behavior of agents, and you can do this reliably and across different domains. Right, so we got a third iteration right here. So 1999. So the core idea, keep the actor-critic mapping, but add an adaptive resonance module. So the system can handle novelty, generalization, and discrimination for both appetitive and aversive cues, and a BG consistent basal ganglia consistent circuit, right? So what's new moves beyond pure TD to model how the brain might form categories that the critic can evaluate, explaining dopamine responses to novel stimuli, and then the limits are more architectural complexity, but still not a full account of action selection, timing, or multi-loop BG cortex dynamics, right? So if I'm not mistaken, to be honest, this sounds a lot like some of the precursors to the frameworks within neuromorphic computing as well. So I know, for example, I'm going to briefly bring up this paper right here, right? So the STDP, so spike timing dependent plasticity from synapse to perception. So this is a pretty important key concept in neuromorphic computing, which aims to have a um, much closer representation of the brain and model systems after that. I believe they're anywhere from about, it's claimed that is about 100 times more efficient than traditional computing, which is based around GPUs, at least for AI, the AI market. I have to actually kind of sit down and see some papers and kind of go through some of their experiments to verify those claims. But in any case, even if it's only about, let's say 25 to 50 times more efficient than, traditional computing, that's still a pretty major win, and it's still very, very early. And this, like the neuromorphic framework out of all of those other frameworks I mentioned earlier, so the photonic and the quantum, like the neuromorphic is pretty much the one that's going to be closest to actually having some type of like major breakthrough within a reasonable amount of time, like maybe about like 10 to 15 years. Whereas quantum, for example, even though there has been progress being made in quantum, that's probably not going to be coming into fruition until like, I mean, I would probably say like 2050, right? Because essentially, before even being able to reliably experiment and do certain things within the quantum framework and repeat those actions, basically you need to have like about 5 to 6 other major breakthroughs before you can even get to the point of actually experimenting and validating certain ideas within quantum computing. And on top of all of that, within like traditional academia, for example, I believe it's been about 15 to 20 years where progress has basically stalled out, right? Like it's just kind of recycling the same old ideas over and over and over again, right? There's a lot of like politicization, there's a lot of, infighting, this and that, a lot of cliques. So essentially, that's not really going to be very feasible for the foreseeable future, unfortunately. So. Also, another thing I did want to add, just before I moved on to 2.4, so I definitely do want to look into the adaptive resonance module, just because of basically that there's a idea out there, like it's floating around that essentially a resonance model would be sort of like the next step after, how should you say, like a constant predictor, right? Because again, most of the models on the market right now are based on like the LLM framework, and the LLM framework very loosely is built on the idea of token prediction or generation. And on top of that, we basically have not a linear progression of tokens, but it's essentially predicting tokens over a probability distribution of things, right? So for example, when you're dealing with text, right, and you're trying to predict the next word or to generate the next word, right? Basically, you generate the next word and then it goes through and it looks through all the possible combinations, the letters, words, so on and so forth, and then you can basically manipulate mathematically the probability distribution to sort of narrow down and to actually have the LLM generate text and sentences that actually make sense, even though it's not actually really understanding what's going on. Like there's no deep level of understanding, right? It's just pretty much, I mean, how would I describe it? It's like a probability machine. It's almost like a slot machine, if you can think about it like that, right? All right, so what's new? Bridges dopamine prediction error, learning with observed anticipatory firing and non-dopaminergic areas. Evidence that TD-driven learning can shape broader BG, basal ganglia, cortical dynamics. So what are the limits? So still model free, anticipatory signals are captured, but there's no explicit world model, hierarchy, or credit assignment across rich tasks. And actually, this is pretty much where we're at right now. For example, right we still, for the most part, do not have explicit world models within most of the AI models coming out today. I know, for example, on Nano Banana from Gemini, or excuse me, from Google DeepMind. So they actually did have, I think they were one of the first video and image generation models that actually did have some semblance of a world model. So the idea that the actual AI system is building an internal representation of the world, and they're able to actually sort of gain some level of consistent understanding of the physics behind, what's going on. So it's not just randomly piecing together certain frames and certain concepts and physical objects within the digital space, it's able to actually understand to a certain degree, to a very limited degree. Okay, this is car, this is the TV or this or whatever the case may be, without being explicitly told what all those different objects are. And then from there, it's able to actually generate scenes, images that are consistent and that actually make sense, right? Again, it's still not 100% perfect, of course. There's still some issues with it when you're actually watching videos generated by the Nana Banana. You do notice that there are certain sections of the video that are kind of blurry, that kind of have this weird movement where the fingers are kind of clipping in and out and doing strange stuff like that. However, again, it's pretty impressive just because again there is some level of consistency when it comes to generation of videos, right? Now, there's also some ways of sort of injecting the hierarchy within these models. So basically, the way that I would describe it, because again, there's so many different ways that you can do this, but the way that I would go about doing this is essentially using hyperbolic models, right? So models that are based on, excuse me, models that are based on Riemannian geometry, or excuse me, Riemannian geometry, where essentially you have these manifolds, you have like these crazy, weird looking shapes, and basically you can use these shapes to manipulate how well a neural network learns, and you can essentially infuse hyperbolic geometry into models, and then that'll actually make them generally more effective. Again, it depends on like a ton of different factors, right? So you need to understand the domain that you're working with, whether it's video, audio, if you're doing image recognition, or you're doing some type of actual like robotic control, so on and so forth. And again, just even drilling down further into those different domains, there are like, dozens and dozens and dozens of different paths that you can go down. But again, just the bottom line is the idea is that, again, you have the field of remaining geometry, and then within that field, you can accomplish certain things by, again, having a skilled, I believe they're called geometers. Skilled geometers come in, basically construct these mathematical frameworks based within remaining geometry, and then infuse that into the model that you're using. And then from doing that process, you can essentially have a model that is actually genuinely gaining some level of understanding and consistent understanding across different tasks, so that once you actually assign it a new task, it's not just forgetting the old one. That's also another major issue, which is the issue of catastrophic forgetting, when again you give the model a certain task, all right, it does, relatively okay. You give it a new task and then basically forgets completely about the old task. And then if you want to circle back around and maybe modify what it did before, then basically it's just gonna, hallucinate and not remember, and you're basically just gonna have to start over from scratch. And that's again another major issue that still has yet to be, fully solved.